Every story has a beginning. But what if the story of our universe doesn't? We've managed to trace our cosmic history back an astonishing 13.8 billion years. We can see all the way to a single, infinitely hot, condensed point that seems to be the origin of everything. We call it the Big Bang. It feels like the first chapter of space and of time itself. But this brings up maybe the most profound question in all of science. What happened in the moment before that? What was there before time began? The journey to find an answer isn't for the faint of heart. It takes us to the very edge of reality, to a time before the laws of physics, as we know them, were written. It's a time when the line between something and nothing blurs into a fog, and the truth of what came before is far stranger than you might imagine. Before we can step into the before, we have to ground ourselves in what we actually know. Our story starts not with a guess, but with an observation. In the 1920s, the astronomer Edwin Hubble discovered that distant galaxies were all rushing away from us. And the farther away they were, the faster they were going. The best way to picture this is to think of a loaf of raisin bread rising in the oven. As the dough expands, every raisin moves away from every other raisin. No single raisin is the center. It just looks that way from its own perspective. Our universe is the dough, and the galaxies are the raisins. The universe itself is expanding. Now, if the universe is getting bigger today, it must have been smaller yesterday. If we run that cosmic film in reverse, all the galaxies, stars, and atoms rush back together until everything is crushed into a single, unimaginably small point of incredible heat and density. That's the Big Bang singularity. Our best piece of evidence for this fiery start is a faint glow that fills the entire sky. It's called the cosmic microwave background, or CMB. It is quite literally the afterglow of creation. This is fossil light from about 380,000 years after the Big Bang, when the cosmos cooled enough for the first atoms to form and let light travel freely. That ancient light has been traveling ever since, its wavelength stretched by cosmic expansion until it reaches us as a faint hum of microwaves. The CMB is a baby picture of the universe. And when we look at it, we see something amazing. Its temperature is almost perfectly the same everywhere we look. This incredible uniformity is a vital clue, but it's also a huge mystery. Here's the problem. When we use Einstein's theory of general relativity to trace the universe backward, it works perfectly, until we get to that very first moment. At time zero, the equations break. They spit out infinity's infinite temperature, infinite density. The laws of physics just stop working. Science has hit a wall. For a long time, the answer to what came before the Big Bang was simply nothing. The question didn't make sense, like asking what's north of the North Pole. But human curiosity doesn't give up that easily. Physicists knew the singularity wasn't a real beginning, but a sign that our theories are incomplete. It was a signpost pointing toward a deeper reality. So, how do we peek behind that wall? The clues, it turns out, were hidden in the problems the standard Big Bang model couldn't solve. The first is the horizon problem. Think about the perfectly even temperature of the cosmic microwave background. How did regions on opposite sides of the sky, which were seemingly too far apart to have ever been in contact, end up at the exact same temperature? It's like two people who have never met showing up to a party in the exact same obscure costume. It makes no sense, unless they both got the same instructions beforehand. The second is the flatness problem. The shape of our universe depends on its total density. For decades, our observations have shown that space is incredibly, exquisitely flat. A flat universe is an unstable state, like a pencil balanced on its point. Any tiny deviation from perfect flatness at the beginning would have been magnified over 13.8 billion years. For it to be so flat today, the initial density had to be fine-tuned to a ridiculous degree of precision. In 1980, a physicist named Alan Guth proposed a wild idea to solve these problems. He called it cosmic inflation. He suggested that in the very first flicker of a second, the exact timing is still debated by physicists, but is thought to be around 10 to the power of minus 36 seconds. The universe went through a period of hyper-accelerated expansion. This wasn't the gentle expansion we see today. It was an exponential explosion of space itself. In a fraction of a second, an area of space smaller than a proton could have ballooned to the size of a grapefruit. This happened because of a hypothetical energy field that drove space apart, often called the inflaton field. While inflation is a leading theory, it's important to remember we haven't yet found direct evidence of this field. Before this violent expansion, the entire observable universe was a tiny, connected patch that had plenty of time to reach a uniform temperature. That solves the horizon problem. And just like a balloon's surface appears flatter the more you inflate it, this rapid stretching would have smoothed out any curvature, solving the flatness problem. Then, just as suddenly, inflation stopped. The energy from that inflatoned field was converted into a firestorm of particles and radiation, reheating the cosmos and kicking off the hot Big Bang we know and love. In this story, the Big Bang isn't the true beginning. It's the end of inflation. And here's the most poetic part. The quantum world is never still. It's always fizzing with tiny energy fluctuations. During inflation, these microscopic jitters were stretched to astronomical scales. These tiny ripples became the seeds of cosmic structure. Over billions of years, gravity pulled more matter into the slightly denser regions, forming the vast clusters of galaxies we see today. Every star, every planet, and every one of us might owe our existence to a random quantum twitch in the first moment of time. The theory of inflation is a cornerstone of modern cosmology, but it has a truly mind-bending implication. If it's correct, it might be an eternal process. This idea is called eternal inflation. It suggests that the inflatoned field doesn't stop inflating everywhere at once. In some pockets of space, it decays, creating a universe like ours. But in other regions, quantum jitters could keep it in its high energy, exponentially expanding state. These inflating regions grow so fast that they create more space for new bubble universes to form. In this scenario, our Big Bang wasn't the Big Bang. It was just a Big Bang, our bubble, nucleating out of an endless frothing sea of creation. This is the multiverse. What's more, the laws of physics inside each of these bubble universes could be different. Imagine a cosmic landscape of possibilities, with different values for things like the strength of gravity or the mass of an electron. Eternal inflation could create universes in every possible configuration. There could be universes where stars burn out in an instant, and others where atoms can't even hold together. And then, there are universes like ours, where the constants just happen to be right for life. This offers a potential answer to the fine-tuning problem, why our universe seems so perfectly set up for us. We find ourselves in a universe that can support us simply because we couldn't exist in the others. Now, we have to be honest. This is pure theory for now. We have no way to see these other universes. But the idea isn't just a sci-fi fantasy. For many physicists, it's a logical consequence of our best model for the universe's first moments. It paints a picture where before our Big Bang, there was an eternal, creative engine constantly spawning new worlds. Eternal inflation imagines a before of endless new creation. But another group of theories sees it as a mirror image of our own universe's future. What if our universe is just the latest in an eternal cycle of birth, death, and rebirth? This is the core idea of the Big Bounce. In these models, the Big Bang singularity wasn't a beginning from nothing, but a transition, the moment a previous collapsing universe bounced and started expanding again. One of the most elegant versions of this idea comes from the Nobel laureate Roger Penrose, who calls it conformal cyclic cosmology, or CCC. His model doesn't need a big crunch. Instead, it uses the ultimate fate of our ever-expanding universe as the seed for the next one. Over trillions upon trillions of years, all the black holes in our universe will evaporate into a cold, empty soup of massless particles like photons. And here is Penrose's stroke of genius. In a universe with only massless particles, concepts like time and distance become meaningless. A photon doesn't experience time. Without anything to act as a clock or a ruler, the universe loses its sense of scale. The infinitely large, cold future of one universe becomes mathematically identical to the infinitely small, hot, dense state of a new Big Bang. The end of one eon, as Penrose calls it, smoothly becomes the beginning of the next. This isn't just philosophy. Penrose argues that the final gasps of supermassive black holes from a previous eon would leave faint circular patterns of heat in the CMB of our own universe, which he calls Hawking points. Penrose and his team have claimed to find hints of these points in our data. It's important to say that these findings are highly controversial and have not been accepted by the wider scientific community, with many analyses suggesting the patterns are just random noise. Still, the idea of a cyclic universe holds a powerful allure, suggesting the moment before our Big Bang was the dying breath of a universe that came before. So far, our theories have mostly stayed within our familiar 4 dimensions. But what if our universe is just a shadow of a richer, higher dimensional existence? This is the strange world of brain cosmology, an idea born from string theory. It proposes that our entire 4-dimensional universe is just a brain, a membrane floating in a higher dimensional space called the bulk. Imagine you're a 2D creature living on a sheet of paper with no concept of up or down. We might be like that, unaware of the larger reality our universe drifts through. In this model, called the ekpyrotic or Big Splat model, the Big Bang wasn't a singularity, but a collision. There are other parallel brains floating in the bulk, and our Big Bang happened when our brain smashed into another. The colossal energy from that crash was converted into the hot fireball of our universe. This model avoids the troubling singularity of the standard Big Bang and provides a natural explanation for the universe's uniformity. A related, though more speculative, idea is that our universe exists inside a black hole. It sounds like science fiction, but the math describing a black hole's event horizon looks strangely similar to the math describing the edge of our observable universe. The theory suggests that when matter collapses into a black hole in a parent universe, it might rebound and create a new expanding universe on the inside. This is definitely a fringe hypothesis, but it's a fascinating example of how scientists are thinking outside our 4-dimensional box. These ideas paint a picture of a before that was a quiet, higher dimensional existence, shattered by a collision that gave birth to our world. So, which is it? A moment of hyper-expansion? One bubble in a cosmic foam? A cosmic rebirth? A collision of worlds? The honest answer is, we don't know. And that's the most exciting answer in science. Each of these ideas is an attempt to solve the same problem. That singularity at time zero, or our physics breaks down. This isn't an end to the questions. It's the starting gun for a new race to find a deeper theory. The goal is to find a complete theory of quantum gravity, which would finally unite Einstein's world of the very large with the quantum world of the very small. The moment before the Big Bang is the one place where the entire universe was both astronomically massive and subatomically small. That's the Planck era, a time of such extreme energy and density that space and time themselves may have been a chaotic quantum foam. The debate is very much alive. Even inflation, the leading model, faces challenges. For instance, the expansion rate of the universe today seems to be faster than our models predict when we look at the early universe, a puzzle known as the Hubble tension. Some research teams using the James Webb Space Telescope have recently presented data suggesting this tension might be resolved, while others find it persists, so the mystery continues. And new ideas are always emerging. A team led by Raul Jimenez at the University of Barcelona proposed in 2025 that quantum fluctuations of spacetime, itself gravitational, waves could be enough to explain the universe's structure without needing a special inflaton field at all. This quest touches on the deepest questions of our existence. Where did all of this come from? Was there a beginning, or has something always been here? We are a piece of the universe that has woken up, a collection of stardust that can now look back at its own origin and ask, how? The answers may be hiding in whispers of gravitational waves from the dawn of time, or in the fine details of the cosmic microwave background. We may never know for sure, but the pursuit itself changes us. It fills us with a profound sense of wonder. We are children of the Big Bang, looking back at the flash of our own creation and daring to ask what came before the light. If you find these journeys to the edge of what we know as fascinating as we do, consider subscribing. There are always more mysteries to explore, and the next discovery could be just around the corner. Thank you for listening.